Okay, let's get to the other type of indeterminate form. So we've been talking about 0 over 0. The other type that you're going to see is infinity over infinity. And so notice here I'm taking the limit as x approaches infinity. And so if I evaluate the numerator, really again I want to focus on my dominant term. If I plug in infinity to that, that is going to approach negative infinity. And into the denominator, think about like plugging in a super big number into 3x squared. That's going to end up going to infinity as well. You can also think about end behavior as far as like sign of the leading coefficient and evenness of the degree. That might help you, but you can also just think about plugging in a large positive number, or if it were as x approaches infinity, negative infinity, a large negative number. So when I see negative infinity over infinity, any type of infinity over infinity, that is an indeterminate form. Which means I get to use L'Hopital's rule, which makes me very happy. And so I'm going to take the derivative of the top and the derivative of the bottom. So negative 4 minus 10x over 6x minus 1. And then I evaluate that as x approaches infinity as well. And so what I notice here is if this is approaching infinity, or x is approaching infinity, my numerator is going to approach negative infinity. So negative 10 times a really big number is going to be a large negative number. 6 times infinity would approach infinity. So that's another indeterminate form. So I get to use L'Hopital's rule again. And so the derivative of the numerator is negative 10x. Derivative of the denominator is 6. Negative 10 and 6. And the limit of a constant is just that constant. I'm just going to simplify it, negative 5 over 3. Now you might be saying, Ms. Paulin, why did I do all that work? I already know how to do this limit without that. You would be right. So if you remember your top-heavy, bottom-heavy rules, you could have said, oh, well, the leading coefficient in the numerator is negative 5. The denominator is 3. Those have the same degree. And so I can just do the ratio of those leading coefficients. So notice that's that same answer down here. That is okay. And on the AP test, even if this came up in a free response, you could just go straight to this step. But in some problems, like number 9, it's not as easy to tell. So if I don't have a polynomial in my numerator and denominator, that's going to be more complex. Now you can still use growth rates and know if you're thinking about which of these is top heavy or bottom heavy, this is going to be bottom heavy because exponential functions, e to the x, grow way faster than polynomial functions. But if you're not sure, again, try to use L'Hopital's rule. So if I evaluate this as x approaches infinity, that's going to approach infinity. And e to the infinity is also infinity. So I'm going to take the derivative. Derivative of my numerator is 8x minus 5. The derivative of my denominator is 5e to the 5x plus 1 over x. And now I'm going to evaluate that as x approaches infinity. So 8 times infinity minus 5, still going to approach infinity. 5e to the 5x plus 1 over x, that's going to approach infinity. One thing you want to keep in mind, a number over infinity is going to approach 0 because it would be bottom heavy. So a number divided by infinity is 0. So this 1 over infinity really acts like a 0. So when I see that I have infinity and infinity, that tells me I need to use L'Hopital's rule again. The derivative of the numerator is 8. Derivative of the denominator, 25e to the 5x minus 1 over x squared. So that was x to the negative first. Derivative would be negative x to the negative second, or minus 1 over x squared. So when I evaluate this as x approaches infinity, what this is really acting like is 8 in the numerator, that's going to stay 8. And 25e to the infinity is going to be a super big infinity. Minus 1 over infinity is 0. So I have 8 over infinity. That's not an okay answer. That's not actually a number. It's just something we think about. And so if you pay attention to my note up here, a number divided by infinity, that limit is going to be 0. Now I can tell in this expression that it's bottom heavy for sure. And so when a rational function is bottom heavy, that limit as x approaches infinity would be 0. Let's try some AP style problems now. So number 10 looks super scary, but remember that always when you're finding limits, your first step is just to plug it in. Try it out, see what you get. So if I plug in x equals 2, I'm plugging that into this x, right? Limit as x approaches 2. So I have the integral from 2 to 2 of e to the t squared minus 1 dt. That has to be 0. I don't have to do any work here. I recognize that these bounds are the same. Automatically that integral is 0. And if I plug in 2 to the denominator, I have 2 cubed minus 4 times 2. That's 8 minus 8, which is 0. So I recognize that I have 0 over 0, which tells me I can use L'Hopital's rule for this limit. You have to check that first because they might put problems on here that look like L'Hopital's rule, but they're not actually. So when I take the derivative of the numerator, this is where I have to use that second fundamental theorem of calculus. So I take the derivative of an integral. That basically cancels each other out. Then I'm going to take my x. I'm going to plug it in for my t. So I have e to the x squared minus 1. And then I would multiply by the derivative of x, but that's just 1, so I don't have to write it. And then the derivative of the denominator is 3x squared minus 4. And now if I evaluate that at 2, I have e to the 4 minus 1 all over 12 minus 4, which would give me e to the third over 8. So not too terrible. It looks a little scarier than it actually was. Number 11 is hopefully a problem you already know how to do. We've gone over it before. So you recognize this formula hopefully as the limit definition of the derivative. So the limit as h approaches 0 of f of x plus h minus f of x all over h. And so it would help you if you recognize I'm trying to take the derivative. My function is sine of x, and I'm evaluating it at pi over 3. And so the derivative of sine is cosine, and then I'm going to evaluate it at pi over 3, and cosine of pi over 3 is 1/2. Now, the other way you could do this is you could use L'Hopital's rule. So if I plug in h equals 0, that's going to go away. So I'd have sine of pi over 3 minus sine of pi over 3. That's 0. H approaches 0, so h is 0. So I can use L'Hopital's rule here. But I have to say when people use L'Hopital's rule, a lot of times they make a mistake. And so this sine of pi over 3 plus h, well, the derivative of that is, sorry, I started writing the wrong thing, cosine of pi over 3 plus h. I would multiply by the derivative of the inside, but that's just 1, because the derivative of h is 1. But then the derivative of minus sine of pi over 3 is 0, because sine of pi over 3 is just a constant. It's radical 3 over 2. Even if you forget what it is, you've got to remember that it's a constant. The derivative of the denominator, h, is just 1. And so then I can evaluate this at 0. So I have cosine of pi over 3, which is 1/2. So notice I really ended up doing the same work that I had done up here, just in a little bit different format. So it's up to you which method you prefer. I prefer this first way up here, but if you like L'Hopital's rule better, then by all means use it. The last problem is a free response. It has a mix with these differential equations we've been talking about lately. So it gives us this differential equation. Now it talks about g being the particular solution to this equation. That does not mean that I need to find the particular solution. It just is telling me that it is. It's basically the y that I would solve for when x equals -1 and I get y equals 2. So don't do separation of variables, anything like that. You can't even separate this one. What it's asking me for is to find this limit. So I'm finding the limit as x approaches -1 of g of x minus 2 over 3 times x plus 1 squared. Now, I have a feeling that this is L'Hopital's rule, and so I might start out just by writing those limits separately. So remember that on the AP test, we want to write these limits out separately, the numerator and the denominator. So this is g of negative 1 minus 2. I know that g of negative 1 is 2. That was given to me. So 2 minus 2 is 0. And then if I also take the limit as x approaches negative 1 of 3 times x plus 1 squared, I get 3 times negative 1 plus 1 squared, which is going to give me 0 as well. So I know then that I can use L'Hopital's rule. So I'm going to rewrite this limit here. Just to make it clear, you're going to make it extra clear what things you're setting equal to each other. I'm going to set that equal to, with L'Hopital's rule, the limit as x approaches negative 1 of g prime of x. The derivative of minus 2 is just 0, so I have just g prime on the top, over 6 times x plus 1. Now, what is g prime of x? Well, we know y equals g of x is this particular solution to this dy dx, which means it's basically the y in this equation. And so what that means is this equation up here is really our g prime of x. It's just a fancy way of saying it. So let's go ahead and plug that in. X squared minus 1/2 y over 6 times x plus 1. Now, we're not sure if we can get an answer here or use L'Hopital's rule, so you might want to go ahead and just write your limits separately when you're evaluating it. It's up to you. So for x, I can plug in negative 1. For y, that's this 2. So negative 1 squared is 1, minus 1/2 times 2, that's minus 1. I get 0. Here, the limit as x approaches negative 1 of 6 times x plus 1, also equal to 0. That means I'm going to have to use L'Hopital's rule again. So this limit here is going to be equal to, I'm going to use L'Hopital's rule, limit as x approaches negative 1. The derivative of x squared is 2x. The derivative of minus 1/2 y is minus 1/2 dy dx. And the derivative of the denominator is just 6. Let's plug that dy dx back in now. Now, if you paid attention, we had actually just plugged in what our derivative was at negative 1. It was 0. And so when I evaluate this, I have 2 times negative 1 minus 1/2 times 0, because that x squared minus 1/2 y was 0, all over 6. Or you can plug in the negative 1 and the 2 again, that's fine. And so that simplifies then to just negative 2 over 6, which gives me negative 1/3. Of course, on the AP test, you could leave your answer right here. You just have to make sure that you don't get 0 over 0 or some other indeterminate form, that you actually have a finite answer. And that's it.